ସାର୍ କିଛି ବି ଭଏସ୍ ଆସୁନି। ହ୍ୟାଲୋ।
हेलो। हेलो।
ସାର୍ କ୍ଲାସରେ ନାହାନ୍ତି ବୋଧେ ଆଉ।
Hello, sir. Sir, are you saying something?
हेलो।
यस सर।
नहीं नहीं, सर नहीं हूँ, मैं सर पूछ रहा हूँ है या नहीं।
वो तो हमें भी पता नहीं।
ठीक है ना, इसीलिए पूछा मैंने।
Sir, sir,
Audible?
yes, sir.
Yes, sir.
So actually, I think you have gone through the things I have taught you yesterday. Today we shall discuss the group theory. Before that, we have to discuss some basic concepts. You know what a set is. So anybody, what do you mean by set?
Group of elements.
Yes. So you know, set is a collection of objects or collection of elements. What you have said in now. Okay. And most importantly, the set of objects or elements must be distinct and distinguishable. Distinct and distinguishable. And the object named X belong to a set when you have those objects distinct and distinguishable. And you can write X belongs to S if S is an object or element in the set S. Okay? And you can read it as X belong to S or X is in S. And if we want to express that some object Y does not belong to S, you can write Y does not belong to S or Y is not in S. Okay? In general practice, to write the elements or description of elements within curly bracket when defining a set. So the word distinct and distinguishable is very much important. And the collection which contains three integers, 1, 2, 3, but with one of them repeated. Suppose you have 1, 2, 2, 2 written in a curly bracket. It is not a set. So in a set, you can repeat one element twice, thrice, or multiple times. You have to write one element once. You know it in your +2 classes. I am just refreshing your memory. The objects of a set can be of any type. For example, sets themselves can be objects and therefore elements of some other set. So it is very important to understand the conceptual difference between an element and a set. Let X be an object, then a set containing this single object, capital X is equal to X, which is in curly bracket, is a set. And a set containing the set X is Y is equal to X in curly bracket, and this contains your X. And Y is another set, you can write X belong to X, and this is in curly bracket X. But X does not belong to double curly bracket X. So, you know, R represents the set of all real numbers. Z represents the set of all integers, positive, negative, or 0. Z0 represents the set of all positive integers, not including 0. 1, 2, 3, 4, so on and so forth. 0, 1 nahi hota hai. C represents the set of all complex numbers. So, very often a set is described by a common property that its elements share. Let R be the set of all real numbers which are positive. Then we can write R plus, R subscript plus is equal to X such that X belongs to R where X is greater than 0. So, the use of curly bracket and the vertical bar in the notation you can have. If there are only a finite number of elements, then you can write their names within curly brackets separated by commas. For example, capital S is equal to N such that N belongs to Z0 and N is smaller or equal to 5. So if N is smaller or equal to 5, then the numbers greater than 5 are not in the set. So you can write 1, 2, 3, 4, 5 are the elements of that set, and that those can be written in a curly bracket. And it is important to know that when a set is written like this, the order in which the elements of the set are written does not matter. It is the same set irrespective of the order. So capital S is equal to in curly bracket 1, 2, 3, 4, 5 is equal to in curly bracket 5, 2, 4, 3, 1 is equal to in curly bracket 3, 2, 1, 4, 5. It is useful to define a special set denoted by phi, which is called empty set. So in empty set there is no elements. There are no elements. So let us give the definition and standard notation of some sets. Suppose R is in the set of real number, then 1, 0 is equal to X belongs to R, such that 0 is smaller than X, smaller than 1, so on and so forth. And
Hello, sir.
open,
Sir,
okay.
listen to me. Hello.
हाँ बताइए
सर सर ब्लैक बोर्ड यूज होने की वीडियो आसुनी
नहीं आ रहा है
नहीं आ रहा है
बट दिख रहा है ओके लेट अस स्टॉप शेयरिंग then share screen. Is it visible now? Is it visible now?
नहीं नहीं विजिबल नहीं हो रहा है।
मैं डिस्कनेक्ट होकर फिर
शायद
कनेक्ट।
शायद
हाँ
उनका
बताइए।
नेटवर्क प्रॉब्लम है।
क्यों आ रहा है?
जी
वीडियो नहीं आती।
Is it visible now?
Yes, sir, visible.
Okay. So there might be some internet problem. So now it is visible. So there are open interval, semi-open or semi-closed interval and closed intervals. So in open interval, in both sides you have normal, you have the symbols like this 0, 1. This is in open interval. So semi-open and this is 0, 1. Though the square bracket represents closed one and other is open one. So this is semi-open. So in semi-open interval, you have in left hand side you have a bracket, and in the right hand side you have a square bracket. In semi closed, in the left hand side you have a square bracket, and in the right hand side you have a bracket. So semi open and semi closed interval. So your x1 and x2, if a open interval, then you can write x belongs to R, where such that x1 smaller than x smaller than x2. Then what are the subsets? If all the elements of T are the elements of S, but all the elements of S are not the elements of T, then you can say T is the subset of S, and S is the superset of T. And you can have your S contains T in a superset notation, and T is contained in S in a subset notation. So intersection, union, and complement of states. Intersection, what is intersection? Suppose there are 5 elements in A. There are 7 elements in B. Out of those, 3 and 4 are 2 elements which were there both in A and B. So in A intersection B have elements, these 2, which are both there in A and B. So A intersection B is equal to B intersection A. Okay. So if you have 2 elements 3 and 4 in A, common in A and B. In A there is two elements like 2 and 3, and in B you have 2 elements like 2 and 3. Then A intersection B will contain 2 and 3, and your B intersection A will contain 2 and 3. So your A intersection B is equal to B intersection C. If there is no common elements in these two states, then the intersection will give a phi set. So A intersection B is equal to phi. And if A intersection B is equal to phi, we can say that A and B are disjoint or mutually exclusive if their intersection is a null set. Similarly, A union B is equal to B union A. And your A union B union C is equal to A union B union C. Okay. So there are Venn diagrams shown in the figure. So in Venn diagram, you can represent intersection, union, and your other things. So see how in intersection B will be represented in a Venn diagram. In the solid part A intersection B, this is your intersection in a Venn diagram. And A union B C. All the elements in A and B are there in A union B. Okay. So you can see the deep lines A union B. Here also deep line represents A intersection B. And there are some identities. A union B is equal to A intersection A is equal to A minus A is equal to phi, A union B intersection C is equal to A union B intersection A union C, A intersection B union C is equal to A intersection B union A intersection C. Then your Cartesian product. If two sets X and Y, we can define a set called the Cartesian product of X and Y and denoted by X cross Y as the set whose elements are all ordered pairs X comma Y, where X belongs to capital X and Y belongs to capital Y. So your X cross Y is equal to X comma Y, such as X belongs to capital X and Y belongs to capital Y. Okay. Then a relation R defined on a set X is a subset of Cartesian product of X with itself. And given an equivalence relation defined on a set X, we can define subsets of X such that every member of a subset is related to every other member of the same subset and not related to any member of the other subsets. Then a function or a mapping f from a set X into a set Y is a rule by which every element X is assigned a unique element of Y. It is important to note that there is only one element of Y which is assigned to a given element of X. Of course, there may be more than one element of X which are assigned the same element of Y. And two simple examples of mapping are the identity mapping. Ix of a set X into say itself maps every element X into itself. The constant mapping maps every element of X into a same fixed element of Y. Okay. Then examples of mapping and range and domains of a mapping. In a mapping, f such that X to Y from the set X into Y, each element of the set X is mapped to some unique element, that is its image f of X belongs to Y. But it is not necessary that every element of Y is the image of some element X. The subset R is a subset of Y consisting of all those elements of Y which are and the image of some element of X is called the range of the mapping F. So R is equal to Y belongs to capital Y such that Y is equal to Fx for some X belongs to capital X. And you are asking about domain and range. I told you that we shall discuss it in later class. So let us see the range, and your range will be Y belongs to capital Y such that Y is equal to Fx for some X belongs to X. And sometimes it is more convenient to choose a subset D. D is a subset of X, and we choose to only map D into Y such that F such that D into Y, and in that case D is the domain of the mapping F. There is into and onto mapping, which you have already known. For a mapping F such that X tends to Y, we generally say that the mapping F maps X into Y. If the range of the mapping F such that X tends to Y is equal to the whole set Y, we say that the mapping is onto or surjective. And if each element X belongs to capital X is mapped to a separate element of Y, then we can say the mapping is one-to-one or injective. And a mapping or a function which is both one-to-one and onto is called one-to-one correspondence or a bijective mapping. The inverse mapping or a function can only be defined for a bijective mapping. Then composition of mappings and inverse mapping. If a mapping F is one-to-one correspondence, that is one-to-one and onto or bijective, then it is possible to define the inverse mapping because there is exactly one element X belongs to capital X. For every element Y belongs to Y, we can then define for each Y is equal to F of X in the inverse mapping. Your F inverse such that Y to X, your F inverse is equal to X. And your F and F inverse and F inverse for F are the identity mapping of sets Y and X respectively. And your F and F inverse and F inverse for F are the identity mapping of sets Y and X respectively. And your F and F inverse are the identity mapping of sets Y and X respectively. And your F and F inverse and F inverse for F are the identity mapping of sets Y and X respectively. Then you know groups in your UG physics, and you know from UG physics courses that if a rigid body is symmetric about an axis, then the rotation by an angle theta about the axis does not change the state of the body. Further, a rotation about the same axis by an angle phi also leaves the state unchanged. This shows that the rotation by theta plus phi does not change the state. So the inverse rotation by minus theta and no rotation, that is rotation by an angle 0, do not change the axis. The group of rotation by all angles is mathematically also a group. And a binary operation B on a set X is a rule by which any two elements of the set are assigned a third element of the set. So we can say that a binary operation is a mapping from the Cartesian product x cross x into x. So the sum of a plus b of two real or complex numbers is a binary operation on the set of real or complex numbers. Similarly, the multiplication of two real or complex numbers is a binary operation. Multiplication of two square matrices is a binary operation defined on the set of all square matrices of the same size. A binary operation x1 or x2 defined on a set X is called associative if for any three elements x1, x2 and x3. And the binary operation is called commutative if for any two element x1 and x2 your x1 x2 is equal to x2 x1. And a group G is a set with a binary operation which satisfy the following three conditions. The operation must be associative. There exists a unique element E belongs to G called identity, such that for any G belongs to capital G, your the expression shown in the screen will satisfy. And for every G belongs to capital G, there exists a unique element G inverse belongs to capital G called the inverse of G, such that the expression shown in the screen is satisfied. So you know group multiplication law and group composition law. This I am showing you group multiplication tables in the screen. A group with only a finite number of elements is called a finite group, and the number of elements of a finite group is called its order. A group which has an infinite number of elements is called infinite group or a group of infinite order. Similarly, commutative or abelian groups. In general, in a group multiplication, the order of elements matters, and these two elements commute with each other. When all elements of a group commute with each other, we call such group a commutative or abelian group. And a group which is not abelian is called non-abelian group. All groups given in the example so far are abelian groups, and it can be proved that all finite groups of order less than equal to 5 are abelian, having order 1, 2, 3, 4 or null 0. A subgroup is a group within a group with the same binary operation. So let G be a group and S a subset of G if the set S has the following properties. First, it is closed under binary operation of G, and second, since the identity must always be in a group, it includes the identity your E belongs to S. And the third is if A belongs to capital S, then A inverse belongs to S. Then you know trivial subgroups and proper subgroups. Then permutation of group or symmetry group Sn is shown in the screen, and if you have any doubt, you can ask. And the permutation group of 3 objects is called symmetry group S3, and a permutation group of n objects is called symmetry group of Sn. And as per permutation, as a permutation is a mapping, the notation, for example, as shown in the screen, can also be written as a 2 and 3, 3 to 1 in a matrix form. Then S3 group and is geometrical illustration Consider an equivalent triangle with vertices numbered as 1, 2, 3. The first triangle denotes the unchanged position of triangle and corresponds to the identity small e. The next P4 is obtained by a 2 pi by 3 rotation about an axis passing through the center of the triangle and perpendicular to the plane of the triangle. A further 2 pi by 3 rotation, that is 4 pi by 3 rotation on E, gives P2. Another 2 pi by 3 rotation will bring it back to E. So you can see it in the screen as figure 17.1. The group S3 is related to the symmetries of a regular triangle, and this group is also called dihedral group D3. And there is a SQ, make the multiplication table for this group of 8 symmetries of the square D4. Then transposition and even and odd permutation, and it is shown in the screen. Those which can be written as a product of an even number of transposition are called even permutation, and those which are product of an odd number of transposition are called odd permutation. And for example, 1, 2, 3, 2, 3, 1, your 3, 1, 2 are even permutations. And odd permutation 1, 3, 2, 3, 2, 1, 2, 1, 3, these are odd permutations. Then coset of a subgroup, to take an element A belongs to G, which does not belong to H, and then construct a set H is equal to H such that H belongs to H is a subset of G, and the subset which is obtained by multiplying A to every element of capital H on the left is called the left coset of H determined by A. And this coset H contains A is equal to A because the identity E belongs to H. And it is important to know that although we have denoted the coset as AH because we choose A as the starting point in the construction, all elements in this coset are on the same footing, that is, they are equally qualified to represent the coset. And for a finite group G, we start with an element A different from the identity. So we can construct A, then A, then A belongs to G. It is very traditional to write A as A square and A as A Q, etc. At each state, either A to the power n is equal to E or to a different group element from E and A, because if A to the power n is equal to A, then multiplying A inverse, we get A to the power n minus 1 is equal to E. So if the group is of finite order, that is if group has only a finite number of elements, then for some value of integer n, we stop at A to the power n is equal to 0. And after that multiplying by A will repeat the cycle as E, A square, so on and so forth, A to the power n minus 1. And the set of elements form a subgroup G. And this is all about cyclic subgroups. And you in the screen I am showing you cyclic subgroups of permutation group. And sometimes cycles cycles are omitted when there is no confusion and the permutation of 4 objects. Then homomorphism, it is an important thing. Given two groups G and G dash with binary operation, your O and O dash a mapping phi such that G to G dash is called homomorphism. If for any two elements A comma B belongs to G, if phi A is equal to A dash and phi B is equal to B dash. And then the things are shown in the screen. When the group G dash is the same as G, we call such homomorphism as endomorphism. Then what is isomorphism? If the identity E belongs to G is the only element which is mapped by a homomorphism phi into the identity E dash of G dash, then the mapping phi is 1 to 1. Because if A and B are distinct elements of G and they map to the same element A dash is equal to phi A is equal to phi B, then since phi is a homomorphism, you can write phi A B inverse is equal to phi A, phi B inverse is equal to A dash inverse is equal to E dash. And a homomorphism for which only the identity maps to identity 1 to 1, if it is so happen to be, that is, the range of mapping is all G dash, then the homomorphism is called isomorphism. हम बताइए, विवेकानंद सर आ गए हैं?
राजन ये बोलो पढ़ेगा।
I think Vivekanand sir has not joined. When he join, then I shall stop. And next class will be continued. Am I audible?
Yes, sir.
Yes.
Then conjugation.
Yes, sir.
Two elements A and B of a group capital G are called conjugate of each other if there is G belongs to capital G such that B is equal to GA, G inverse. And the relationship is mutual because we can also write A is equal to G inverse, B, G inverse of inverse. Okay. Then invariant subgroups. An invariant subgroup or a normal subgroup H of a group G is such that all the conjugate elements of H are within H itself. And the description is shown in the screen. Then your matrix representation. If G is a group, then a homomorphism of this group GL n comma R and GL n comma C for some n is called a matrix representation of capital G. And a matrix representation of such a group is a mapping D such that G to M of the group elements into a set of M of real or complex matrices such that the group law is obeyed by the matrix shown in the screen. Then you have two matrix representation of D2 as shown in the screen and in tabular form. I am showing you what happens. Then diagram for matrix representation of D. Then your 3-3 matrix representation of S3. Then equivalent representation.
Sir, are you saying something? Please unmute yourself.
Sorry. Then source lemma. Suppose DG is an irreducible n cross n matrix representation of a finite group, and there is a matrix capital M of the same size which commute with every D which is a function of G, where G belongs to capital G. Then M DG is equal to DGM for every G belongs to capital G. And the source lemma tells us that such a matrix M can only be a constant times the identity matrix. And you can have a brief idea of source lemma by going through the explanation shown in the screen. Okay, there are some terminal questions. You can go through these. Then your continuous groups. So let us wait if Dr. Naik will join. Then he will take his class. If you will not join, then we continue this group theory after a short gap.